In the last class, we were going through some of the basics of linear algebra and matrix theory, right? And in particular, we looked at similarity of matrices and determinants and so on, right? And in today's class, I'll talk about eigenvalues, eigenvectors, diagonalizability, SVD, and positive semi-definite and positive definite matrices. I won't prove everything, but I'll still try to give at least proof sketches of most statements. All right, if you're interested in more details, there are a couple of references in the lecture notes, so you can just go through those. All right. But before we start, any questions? Any questions from last time? Okay, so let's go ahead. Great. So one important notion in linear algebra is that of orthogonal vectors. Right. So given any two vectors, they're said to be orthogonal if their inner product is equal to 0. Right. So U, V are orthogonal to each other if their dot product, which is typically U transpose V, is equal to 0. Right. And they're orthonormal if this is true, and in addition, both have norm equal to 1. Right? So the question is, now suppose I give you a basis for a vector space. Does there always exist an orthonormal basis for this particular vector space? And yes, and how would you find an orthonormal basis for this vector space? Okay, but it's if once you normalize them, they're normal, yes, but how do you ensure that they're also orthogonal to each other?
They need a basis. If we take a basis, so given a basis.
Okay, given the basis, let's say I take R2. Okay, let's take 1, 2, and 2, 1. Do these two vectors form a basis for R2?
Yes.
They do. But are they orthogonal to each other? They're not. So then if I give you an arbitrary basis, how do I get an orthonormal basis out of it? Certainly normalization is not enough.
First we give B1.
Okay.
And for B2 is a slightly orthogonal. We take the transformation like so.
Okay.
B2 orthogonal to B2.
Right. So in other words, so geometrically speaking, you try to find the projection of the, suppose I give you two vectors and I want to construct two orthogonal vectors out of these. What I can do is, well, I have one vector. The second vector, I know that there is some component along V1 and there's some other component orthogonal to V1. Right? So I have this is my V1, and I have another vector, let's call it V2. Now I can always decompose V2 as a vector along V1 and one that is orthogonal to V1. Right? What is this vector equal to? The dot product times. So it is the dot product between V1 and V2 times the vector which is along V1, the unit vector along V1. So V1 divided by the norm of V. Right? And what is this vector equal to? It's just V2 minus the component along V1. So this is V2 minus inner product between V1 and V2 divided by norm V1 times V1. Right? And if I have more than two vectors, I can always keep doing this, right? So I have, let's say I have v1, v2, v3 and so on. So I first start with v1. Take v1. So what do we have? We're given a basis. So I'm given a basis v1 through vn, and my goal is to construct an orthonormal basis from this. So I can take v1 and set u1 to be just v1 divided by the norm of v1. Right? So this ensures that my first vector has unit norm. Now, what about the remaining? Now, suppose I've already obtained, let's say, I minus 1 orthonormal basis vectors, right? So in order to obtain the second vector, all I had to do was find the projection along v1 and then subtract that component out. That gave me the component which is orthogonal to v1. So similarly, if I have I minus 1 vectors, all of which are orthonormal to each other, all I have to do is for vi, I find the projection onto these vectors, I subtract those components out, and the remaining component, whatever remains, is going to be orthogonal to all of those, and then I have to normalize the rest. So I find the component, let me call it ui tilde. This is vi minus right. So this quantity would be the projection onto the vector uj. We've already normalized uj, so I don't have to divide by norm of uj. It's just going to be 1. So I subtract out all the components along u1, u2, u3 up to ui minus 1. I remove that and I get ui tilde. Now all I need to do is just normalize this. So this procedure is called the Gram-Schmidt orthogonalization procedure. Have you all seen this before? Yes? Anyone has not seen this before? Has anyone not seen the Gram-Schmidt orthogonalization procedure before? Okay, so well, this is the Gram-Schmidt orthogonalization procedure. So given any basis, I can always construct an orthonormal basis for this vector space. Right, and this is a fairly efficient procedure, and you can do it quite easily. And what this implies is that given any matrix A, right, you can think of the columns of A as the basis for some subspace, the column space. Now, if I apply Gram-Schmidt orthogonalization procedure, then effectively what I get is that I can decompose the matrix A as a product of an orthogonal matrix, right, times an upper triangular matrix. So given any matrix A, which has, let's say, full column rank, it need not be square. I can write this as an orthogonal matrix times an upper triangular matrix. And you can easily verify that indeed what you get using the Gram-Schmidt orthogonalization procedure is basically the QR decomposition. The columns of Q, which is the orthogonal matrix, are basically going to be the orthonormal vectors, the new basis, and you can convince yourself that the corresponding R is going to be upper triangle, right? Okay, so we'll see why this becomes important pretty soon once we look at symmetric matrices. Right? So now given an arbitrary matrix A, let's say n by n matrix, I want to know if I can diagonalize this particular matrix. Right? But what does that mean? So recall that a vector V is an eigenvector and lambda is an eigenvalue for a particular matrix. If I can write A times V equal to lambda times V. Right? Recall that this is an eigenvalue and V is said to be a corresponding eigenvector. Right? And how do you find the eigenvalues and eigenvectors for a matrix? Yes, what is the characteristic equation? Right, so you look at the following equation, determinant A minus lambda I equal to 0, solve for lambda, and let's say that this has lambda 1, lambda 2 up to lambda k. Let's say that it has k roots, k real roots. These are the eigenvalues. Yes. Yes. Which one is unique? You mean the eigenvalues? So they're unique, yes. For a given matrix A, you have a set of eigenvalues, but they may not be distinct. Right? So some of these roots could be, after all, determinant A minus lambda I is going to be a polynomial. Right? And you're solving a polynomial. The polynomial could have, it need not even have n roots. So if A is an n by n matrix, it need not have n real roots. Some of them could be complex. And I'm assuming that there are k real roots, which are the real eigenvalues corresponding to this particular matrix. Okay. Is that clear? There could be complex eigenvalues, yes, which is fine. So that is why if you're working with a field of complex numbers, then every matrix A has n eigenvalues. Right? It always has n complex eigenvalues because given any polynomial, you can always find n roots, right, over the field of complex numbers. But then over the reals, you may not be able to find n roots. Right? So let's say that this polynomial, the characteristic polynomial, has k eigenvalues, k real eigenvalues, and potentially these could have different multiplicities, right? So for example, each lambda I could have multiplicity let's say alpha I. So in other words, lambda I repeats alpha I times as a root in the characteristic polynomial. Correct. So this multiplicity is sometimes called the arithmetic multiplicity of the eigenvalue lambda I, or also called the algebraic multiplicity of lambda. Okay, so let's just keep this object in mind. So the number of times lambda I repeats as a root is called the arithmetic or the algebraic multiplicity. Now let's look at the set of all eigenvectors corresponding to an eigenvalue. Right, so I'll define Vi as the set of all vectors V such that A times V equal to lambda I times V. Okay, now of course there could be multiple eigenvectors, right? But what can you say about this set? Does it have some nice properties? It's a vector space. Does everyone agree? Yeah, you have to well, this is automatically satisfied, right? Yeah, so again, whether you call, I don't say that vi is an eigenvector, so 0 is an eigenvector, but it certainly does satisfy the following equation, that a times v equal to lambda I times. Okay, so this forms a vector space. Why? Yeah. Okay, again, do you have to verify all the properties? Do I have to verify all the 7 properties to convince myself that this is a vector subspace? All I need to do is just check for whether it's closed under linear combinations, right? And that's easy to verify, because if I have alpha v1 plus beta v2, and I take a times alpha v1 plus beta v2, then this is equal to alpha times lambda alpha times av1 plus beta times av2, but v1 and v2 are in vi, so this is alpha lambda I v1 plus beta lambda I v2, which is just lambda I times alpha v1 plus beta v2. So this also lies in vi. So it's a vector subspace. Now the dimension of this vector subspace is what we call the geometric multiplicity of corresponding to the eigenvalue lambda I. Okay, so if I take any vector in vi and apply a, what does the linear transformation corresponding to a look like when I restrict it to just this, let's say, subspace? It's scaling, or in other words, it looks something like a diagonal multiplication by a diagonal matrix. It's just plain scaling. Now suppose I could construct a basis for Rn purely out of eigenvectors. Then in that basis, what does the linear transformation A look like? Yes, so what is the structure of the matrix? It's just going to be a diagonal matrix with eigenvalues. So if we can construct a basis for Rn out of eigenvectors, let's say v1 up to vn, then A represented in terms of this basis is diagonal. Right? and the diagonal entries are just going to be the corresponding eigenvalues. Right? So remember that two matrices are similar if I can write A as, let's say, P, B, P inverse, right? And what is the matrix P? What are the columns of P? Yeah, so they are essentially the new basis vectors. And what is the matrix B? It is simply the linear operator, how the linear operator A operates on the new basis vectors. So if I can construct a basis purely out of eigenvectors, so if I can find n linearly independent eigenvectors, then I can write A as P, D, P inverse. Right? So in other words, in terms of the geometric multiplicity and the arithmetic multiplicity, what kind of conditions would we require? Yeah? Okay, is that sufficient?
Depends on the like, if you have
Yes.
complex
So we're operating purely on the real number.
all the eigenvalues are.
Yes. So in other words, the sum of the algebraic multiplicity should be equal to n, and the geometric multiplicity should be equal to the arithmetic or algebraic multiplicities. But this in general is not possible. Right? So for example, can you give me an example of a matrix which is not diagonalizable? Or a case where the arithmetic multiplicity is not equal to the geometric multiplicity? Okay, so let me give an example. Let's take the following matrix: 1, 1, 0, 1. What are the eigenvalues of this going to be? 1, right? It's a repeated eigenvalue. Equal to 1. So alpha 1 is equal to 2. So the algebraic multiplicity is 2. How do we find the geometric multiplicity?
Find the eigenvalues.
Okay. Yes. So the null space of which matrix? 0, 1, 0, 0, 0. Yes. So basically I look at A minus lambda times I, which is 0, 1, 0, 0. What is the dimension of the null space of this thing? The dimension is equal to 1. So what is the geometric multiplicity equal to? Yeah, it's 1, right? and this is equal to 1. It's not equal to 2. Right? So this matrix is not diagonalizable. Yes. Yes. So if it is, and why is that the case? So what can you say about the geometric multiplicity? How small can it be? How large can it be? Okay, as small as 1. Can it be 0? It cannot be 0. Why is that?
Because determinant of A minus lambda is 0.
It's equal to 0, yes.
It can't be an invertible matrix or
Correct.
a
Yes. So the null space should have at least, yeah, one non-zero vector, whatever. It has dimension at least 1. Right? So the geometric multiplicity so it is greater than or equal to 1. And how large can it be? It can be as large as the arithmetic multiplicity. Right? The sum of the arithmetic multiplicities can only be n. It could be less than that, but it can't exceed n. So if I want to diagonalize a matrix, I have to find a basis of n eigenvectors. Right? And where do the eigenvectors come from? I can only pick them from each of those spaces, right? Each of those eigenspaces. Now from each eigenspace, how many linearly independent vectors can I pick? What is the largest number of linearly independent vectors I can pick from one eigenspace? N? Well, just from here, the quantities that I have over here. Geometric multiplicity, right? I can't pick more than geometric multiplicity number of linearly independent vectors. So if the sum of the geometric multiplicities is not equal to n, then I can't find n linearly independent eigenvectors. But if the geometric multiplicities, if the sum of all the geometric multiplicities is equal to n, then I can find a basis, right? In which case it is diagonalizable, right? Okay. Yeah, so it's one other thing. Of course, there are some steps in between. For example, you have to show that the geometric multiplicity is at most the arithmetic multiplicity, right? That requires a separate proof. Also, each eigenspace is linearly independent of the other. So if I take a vector, if I take an eigenvector corresponding to one eigenvalue, then this is linearly independent of all the other eigenvectors corresponding to all other eigenvalues. Right? That's something you need to prove. Okay. So another useful sort of representation of diagonal matrices or diagonalizable matrices is the following. So I can write, it is possible to write A as lambda 1 E1 plus lambda 2 E2 plus lambda k ek, where the lambda i's are all the distinct eigenvalues, and each ei is basically the projection matrix that projects Rn into the eigenspace corresponding to lambda I. Right? And each of these representations are sometimes useful depending on the kind of problem that you have. What is a projection matrix? What is a projection matrix? U transpose?
Unitary matrix and the projection matrix U transpose.
Why?
So it's basically given a vector, it gives the projection of any given vector onto the space of the matrix.
Okay, how do you say that U transpose is the projection? What is U?
Some unitary matrix.
Okay, why should it be unitary? What is a unitary matrix? Okay. So given a vector space V, how would you find projection? Okay, so suppose I have this operator which I call a projection. I apply the projection 2 times. What do I get? Applying it once. So what is a projection matrix? Just any matrix for which E times E is equal to E, or E square is equal to E. Right? So that's the definition of a projection matrix. Any operator, if I apply it twice, it's the same as applying it once. That is a projection. Okay. So what we are really interested in are these class of matrices called symmetric matrices. So when is a matrix symmetric? A is equal to A transpose. Correct? A nice property of symmetric matrices are that they're always diagonalizable, and we'll see why. So firstly, suppose I take 2 eigenvectors, all right, corresponding to 2 different eigenvalues. So say lambda 1 is not equal to lambda 2. These are 2 distinct eigenvalues, and I look at eigenvectors v1, v2 corresponding to lambda 1 and lambda 2. Okay. So I want to know what kind of properties these 2 vectors have. So let's say that I take v1 transpose A times v2. What is this equal to? What is A times v2? Lambda 2 times v2. So what is v1 transpose A times v2? So it's just lambda 2 times v1 transpose v2. That's fine. Right? Okay, so now let me take the same quantity, but let me take the transpose of the left hand side. What will it be equal to? So it's v1 transpose A times v2, the whole transpose, which is going to be lambda 2 times v1 transpose v2, the whole transpose, which is what? v2 transpose v1, but this is also equal to v1 transpose v2. Okay, this much is fine. Now let's look at this quantity. What is this equal to? This is V2 transpose A transpose V1, right? But what is A transpose equal to? It's equal to A. So this is V2 transpose A times V1. But what is this equal to? This is equal to lambda 1 times V2 transpose V1, which is the same as lambda 1 times V1 transpose V2. Correct? You're all with me at this point? So I've basically taken V1 transpose A times V2 for eigenvectors V1, V2 corresponding to lambda 1 and lambda 2. And on the one hand, it's equal to lambda 2 times V1 transpose V2. And similarly, just by taking the transpose of this and applying the fact that this is a symmetric matrix, I get that this is also equal to lambda 1 times V1 transpose V2. But what do I know about lambda 2 and lambda 1? They're not equal to each other. But lambda 2 times V1 transpose V2 is equal to lambda 1 times V1 transpose V2. So what is the only possibility? So V1 transpose V2 should be equal to 0. Otherwise, this can never be satisfied. Right? So this means that if I take two distinct eigenvalues, then the eigenvectors corresponding to them are going to be orthogonal to each other. This is true for symmetric matrices, but in fact that's a good point that you raised, because it turns out that it's if I can find an orthogonal basis only for symmetric matrices. So that's what is called the spectral theorem, and it says the following. So a real matrix A is symmetric if and only if it is orthogonally diagonalizable. Right? So in other words, I can write A as P dP inverse for some orthogonal matrix P. So if I can write it as P dP inverse, then what is P inverse equal to? If P is orthogonal, it's equal to P transpose. Right? So firstly, let's try to prove the easy part. So if a matrix is orthogonally diagonalizable, then what is A transpose equal to? What is this equal to? So it's P dP transpose whole transpose, which is P D transpose P transpose. But what is D? It's a diagonal matrix. So what is the transpose of the diagonal matrix? It's equal to itself, right? So this is equal to PD P transpose. So if I can find a matrix which is orthogonally diagonalizable, then it must be symmetric, right? But the other way around is not that simple, correct? And it's not entirely trivial, so I won't prove it completely, but I'll give at least a sketch of the proof. So for the other way, so if so suppose that A is symmetric, right? You can prove this via induction. I want to show that this is orthogonally diagonalizable. Okay. So if n equal to 1, then whatever, orthogonality is kind of trivial. It's every 1 by 1 matrix is orthogonally diagonalizable because it itself is a diagonal matrix, right? Okay, now suppose that this is true for all matrices of size n minus 1 by n minus 1. Right, suppose that this is true. I want to show that an n by n matrix is also orthogonally diagonal, n by n symmetric matrix. So take an n by n symmetric matrix A. I'll pick one eigenvalue, one non-zero eigenvalue. Let's call it lambda 1. Okay, and I'll pick one eigenvector corresponding to this eigenvalue. Right? I'll pick an I'll normalize it. Let's say that V1 is a corresponding unit norm eigenvector. Right? Now what do? I'll do Gram-Schmidt orthogonalization of the vector space starting from V1. I don't care what the other vectors are, but I'll pick some orthogonal basis. So I'll take V1, V2, and so on, Vn. V2 up to Vn need not be eigenvectors. Some vectors, but this is some orthonormal basis. Okay.
How do you get V2 to Vn?
I use Gram-Schmidt orthogonalization. I can pick any basis, right, with V1 as one of the basis vectors, and then I do Gram-Schmidt orthogonalization. That will give me a basis, an orthonormal basis. Right? So I can write A as P times some matrix times P transpose. Right, with the columns of P are precisely V1, V2 up to Vn. Now the claim is that this is equal to, this matrix is going to be equal to lambda 1 times 0 times some submatrix. And why is this happening? Why are all the other entries equal to 0? Yeah. Okay, and so you're getting this lambda 1 over here, I agree, but why are the other entries equal to 0?
We assume that they are, for example,
You assumed what?
It's a minus 1 by n minus 1 symmetric matrix. So
No, A is an n by n symmetric matrix, right? A is,
Wait.
okay, this is fine. This is going to be an n minus 1 by n minus 1 submatrix. This entry is equal to lambda 1. Why are these equal to 0? Where do you get this specific matrix structure is the question. Okay, so
Why is that entry lambda 1?
why is that entry lambda 1? Okay, that's also a question. So why is it equal to? I'm taking v1 to be the eigenvector corresponding to lambda 1. Which one?
First time we normal lambda 1.
Why? Why? So what does this basically tell you? So if I take this particular matrix, right, I'm representing vectors in terms of the new basis. Right? Suppose I have a vector which is alpha 1 v1 plus alpha 2 v2 and so on, plus alpha n vn. Basically a times this, what will this be equal to? Okay, that is fine. But in terms of this particular matrix, so remember that this is the linear transformation corresponding to this particular basis, right? So if I take the vector, let me call this b, then b times alpha 1 up to alpha n, this is going to be the vector of coefficients of v1, v2 up to vn when I transform this vector by a. So this will be alpha 1 a v1 plus alpha 2 a v2 and so on. Right? So if alpha 1 is the only component that is non-zero, okay, all the other entries are 0, then what would be the first, what does that tell me about the first column of B? Yeah?
Along v1.
It's along V1, right? And is that what is happening over here? Sorry? All the
will be 0.
Yes.
A1.
So only the first, it's going to be non-zero only along the first component and 0 along all other components. Right? So if I take any matrix A, right? If I multiply by A times B, what is the first column of A equal to? It's equal to A times 1 with all zeros matrix, right? So in the new basis, what does that translate to? It translates to taking alpha 1 equal to 1. So the first column of B is basically going to be, you take the first component of equal to 1 and the rest of the components to be equal to 0, right? And what is that equal to? It's equal to alpha 1 times V1, which in other words should be some scaling lambda times alpha 1 and also. Does that make sense? Why is V? No. So I'm representing things in terms of the new basis, right? What is the representation of V1 in terms of the new basis? It is 1 followed by all zeros, right? And how does the matrix A operate on V1? It just scales it, right? So in terms of the new basis, what is a transformation of V1? Scaling. So it's just lambda 1 times 0, 0, 0, 0, 0, 0, right? And therefore, the first column should be lambda 1, 0, 0, 0, 0. Because after all, this is the matrix with respect to the new basis, right? Similarly, you need to show that these components are also equal to 0.
Symmetric.
Yeah, so it's symmetric. So basically A transpose, what is A transpose equal to? It's going to be P this transpose times this. Therefore, this should be symmetric. So this tells you two things. One, it has this particular structure. And secondly, what about this submatrix over here? What can you say about this submatrix? Yeah, it should be symmetric, right? So this submatrix is symmetric, and it's an n-1 by n-1 symmetric submatrix. What does our induction hypothesis say? n-1 by n-1 submatrices are orthogonally diagonalizable. So I can write this as some orthogonal matrix U times D times U transpose. Taking that out, the product of two orthogonal matrices is also orthogonal, right? And therefore this is some P bar times D times P bar transpose. All right, so it's a bit quick, I know, but you can go through a better reference to go through the proofs in detail. I did it a bit quickly, right? But this is basically the gist of it. There are again different ways of proving the same statement. This is sort of the one which requires least prerequisites. You just use induction. Yeah.
I have a question.
Yes.
We said like a matrix is symmetric if it's orthogonally diagonal.
Yes.
And like before that we said eigenvectors corresponding to distinct eigenvalues are orthogonal.
Yes.
So are all eigenvalues corresponding to a symmetric matrix distinct?
No.
But they'll always be, like the eigenvectors will always be orthogonal.
So okay.
No,
Yes. So and the reason that is because now I have these different eigenspaces, one corresponding to each eigenvalue, right? I know that if I take one vector from one eigenspace, it's going to be orthogonal to every vector in every other eigenspace. But within each eigenspace, I can always find an orthogonal basis. And that's it. Yeah. So you have to be clever in choosing your eigenspace, in choosing your basis for the eigenspace. But I'm guaranteed to be able to find an orthonormal basis. Any questions? Okay, so this means that symmetric matrices have some nice properties. We'll look at an even more specific subclass of symmetric matrices, and those are the class of positive semi-definite matrices. So I'd say that a real symmetric matrix A is positive semi-definite if all its eigenvalues are non-negative. So remember that the previous statement that we just showed, that every real symmetric matrix is orthogonally diagonalizable. This gives us one extra piece of information, and that is the geometric multiplicities are always going to sum to n. Right? I am guaranteed to find all real eigenvalues. Right? So all the eigenvalues corresponding to a symmetric matrix are going to be real. They may be positive, they may be negative, but they're all going to be real. And I'm going to focus on a subclass of those matrices, and that is positive semi-definite. So all the eigenvalues are greater than or equal to 0. Okay. So I'll denote this by this particular notation, a sort of curly greater than or equal to 0. And I'll say that A curly greater than or equal to B if A minus B is positive semi-definite. The reason why we are interested in this class of submatrices is because whenever we solve sort of a large class of convex optimization problems, we can represent many of the constraints in terms of these positive semi-definite or positive definite constraints. Right? And in fact, for such class of problems, wherein you have a convex function, or in many cases a linear function, but with positive semi-definite constraints, you can find very efficient algorithms to solve these. Right? So that's a separate subclass of problems called sort of a separate class of positive definite programs. Right? And you can solve those very, very efficiently, much more efficiently than you can solve generic convex optimization problems. Right? It's called semi-definite programming, SDPs, and there's been a lot of recent interest in this class of problems because many very hard problems can be approximated by semi-definite programs, which can be solved very efficiently in practice. Okay, so this is the class of matrices. It's positive semi-definite if all the eigenvalues are greater than or equal to 0, and similarly it's said to be positive definite if all eigenvalues are greater than 0. And we'll denote this by A curly greater than 0. And again, we have this notion of A curly greater than B if A minus B is curly greater than 0. Right? So you can see that this kind of generalizes inequalities. Right? If I have inequalities of functions or real numbers, I can translate that to a matrix inequality using this particular approach. Okay, so if I have a positive semi-definite matrix A, what can I say about the following quantity, x transpose AX? Yeah, and why?
Vector x can be shown as a linear combination of all the eigenvectors.
Correct. So I can write,
Then separate it, and each term should be greater than equal to linear combination.
correct. So I can write it as a linear combination of the eigenvectors because it's a diagonalizable. We know that symmetric matrices are orthogonally diagonalizable. So I can find an orthonormal basis v1, v2 up to vn such that I can write x in this particular form. Right. So what is x transpose AX equal to in terms of this particular quantity? So what is A times X going to be equal to? Yes, so it's not lambda X, right? So for each of these, I could have a different eigenvalue. So it's X transpose. Yeah, alpha 1 lambda 1 v1 plus alpha 2 lambda 2 v2 so on up to alpha n lambda n vn. The lambda i's may or may not be all distinct. They could be repeated, but doesn't matter. But what do I know about the lambda i's? The lambda i's are always greater than or equal to 0. That's one guarantee that I have. But what is this equal to? Yes, I know that the VI's, yeah, so the VI's are all orthonormal, right? So I have X transpose, which is this transpose. So this will be equal to alpha 1 square lambda 1 norm V1, but norm V1 is 1 because it's an orthonormal basis. Alpha 2 square lambda 2 plus alpha 3 square lambda 3 and so on up to alpha n square. I know that all the lambda i's are greater than or equal to 0. The alpha I squares are always greater than or equal to 0. So this quantity is always greater than or equal to 0. Well, in fact, in many cases, you use this as a definition of positive semi-definiteness, that X transpose AX is greater than or equal to 0 for all X in Rn. And in fact, this is an if and only if condition. So I've used a slightly different definition of positive semi-definite matrices. That is, all the eigenvalues are greater than or equal to 0. Right? But you can show that if this is true, then all the eigenvalues should also be greater than or equal to 0. And it's symmetric. All right. Okay. So a nice property of positive semi-definite matrices is that I can define a square root. So remember that when we try to find the gradient of the log determinant of a matrix, we use this particular property that positive semi-definite matrices have a square root. Right? And that can be very easily seen now that we know what a PSP matrix is. Right? So I have A, which I can write as P, D, P transpose. D is a diagonal matrix and all the diagonal entries are greater than or equal to 0. So each diagonal entry has a square root. So if I look at square root of D, but let's see, let's first take D. It is lambda 1, lambda 2, lambda n. It's a diagonal matrix. Suppose I look at the following matrix, which is P times root lambda 1, root lambda 2, up to root lambda n. Okay, let's look at this particular matrix. What is the square of this matrix going to be equal to? A. Does everyone agree? Because if I look at A half times A half, it's going to be P times this matrix times P transpose. Let me call it lambda half P transpose times P times lambda half P transpose. But what is P transpose P? Identity, because P is an orthogonal matrix. So this is P lambda half P transpose. But what is lambda half into lambda half? It is just this matrix D, and this is equal to P P transpose, which is A. Right? So at least for positive semi-definite matrices, there's a well-defined notion of a square root. But in general, for other matrices, you don't have such a notion. Right? You can't necessarily find a matrix B such that A equal to B square. All right? But what can you say about the square root itself? It is also going to be positive semi-definite, right? Because again, it's orthogonally diagonalizable, and all the eigenvalues are greater than or equal to 0, right? But again, I could have potentially defined the square root in a different way, right? There's no unique square root, mind you, because I could have taken, say, lambda 1 minus root lambda 2 minus root lambda 3 and so on. That's also a valid square root. Do you agree? But I'm choosing the square root in this specific fashion so that I get a nice positive semi-definite square. Okay, and typically when you say the square root of a matrix, it is this matrix that we're referring to. Right? Any questions? Great.
Same is true for a to the power of n.
Same is true for?
A to the power of n also it can be easily.
Yeah. Okay. If A is positive semi-definite, then A square is also going to be positive semi-definite. It is just P D square P transpose and so on. You could potentially define a square root, right? So in principle, a square root is any matrix B such that A is equal to B square. For non-PSD matrices, you could be able to find a square root for some matrices, but not necessarily for all matrices. I'm not aware of something like that, but there could be. But generally, when you're talking about square roots of matrices, it is for positive, at least the way I have encountered it is that. Okay, so all of this discussion was for square matrices, right? Diagonalizability and so on. Now, if I have a potentially rectangular matrix, or if the matrix is not diagonalizable, then what can we do? Now, in that situation, if I have a general M by N matrix A, it is possible to write A as some matrix U times lambda times B transpose, where U and V are orthogonal matrices, and lambda is a diagonal matrix. So if A has rank, let's say T, then this matrix U is going to be an M by T matrix. The matrix V is going to be an N by T matrix, and lambda is a T by T diagonal matrix with non-zero entries, with non-zero diagonal entries. All right. And how do you get U and V? So what happens when I take A transpose A?
Transpose lambda squared.
Yeah,
V transpose lambda squared.
it's going to be a V transpose. It's going to be V lambda square V transpose, right? But what do I know about A transpose A? It's symmetric. Is it positive semi-definite? So this is positive semi-definite because if I look at X transpose AX, this is just norm AX square, which is guaranteed to be greater than or equal to 0. Right, so it's a positive semi-definite matrix, which means that it is orthogonally diagonalizable and all the eigenvalues are going to be greater than or equal to 0.
So we can say it's
Diagonalizable anyway because it's symmetric, that's true, but they're also going to be greater than or equal to 0, and that is what is important, right? Because the singular values, as I'm going to take them, are going to be the square roots of the eigenvalues of A transpose A. For that to make sense, I have to make sure that a square root exists. Just 1 second. Yes. Sorry? You... sorry, I'm not sure. I don't follow. So A transpose A but what is U? U is orthogonal, right? So, okay, let's write down A transpose A. All right, so now I'm sort of going back and forth over here. Suppose that A can be written as U lambda V transpose. Then what is A transpose A going to be equal to? It is U lambda V transpose U lambda V transpose, which is just V lambda U transpose U lambda V transpose, but U transpose U is identity. So this is V lambda square V transpose. Similarly, if you can compute AA transpose, what will this be equal to? It's going to be U lambda square U transpose. Okay. So essentially the singular values are the square roots of the eigenvalues of A transpose A or AA transpose because they have the same eigenvalues. A transpose, the matrix U, the columns of U are what we call the left singular vectors, and the left singular vectors are essentially the eigenvectors corresponding to AA transpose, The columns of V are what we call the right singular vectors, and these are going to be the eigenvectors of A transpose A. Right? And the reason why we can actually represent this in terms of the singular value decomposition, or why do we have the singular value decomposition, is because both A transpose A and AA transpose, they're symmetric, they're positive semi-definite, and therefore they're orthogonally diagonalizable. All the eigenvalues are greater than or equal to 0. So you can show that, I mean, it's not too hard to see why you can construct U and V such that you can write A as U lambda V transpose. So in some sense, you're getting the singular value decomposition from the square roots of A transpose A and AA transpose.
What situations we use this decomposition?
The singular value decomposition. So in many cases, when you want to, let's say, find matrix power, so you want to multiply two matrices, right? So in many cases, for specific subclasses of matrices, you can do the singular value decomposition much faster than, say, doing matrix multiplication. So even if you want to do matrix multiplication, at times it's more easy to find the singular value decomposition and then do matrix multiplication. And that was really one of the original motivations of doing diagonalization itself. Suppose I want to find A to the 100, right? How do I do this efficiently? Computing A into A into A into A using brute force is a very inefficient approach. But suppose I can diagonalize it. Then what is A to the 100 equal to? It is just P D to the 100 times P transpose. So there's just 3 matrix multiplications involved over there instead of 100 matrix multiplications. So that makes it very efficient. In fact, you can compute any matrix polynomial using very efficiently if you can diagonalize the matrix. You can compute, also have this notion of matrix exponential, right? E raised to the A, because you can write e to the x as a Taylor series approximation, right, which is basically a polynomial series. And now matrix polynomials make sense, so therefore Taylor series of matrices can also potentially make sense if these things converge, and so on. Right? So all of these decompositions, matrix decompositions I mean, there are separate reasons, because these tell you some geometric or linear algebraic properties which could be useful in some other problem. But one of the strong motivations for studying these various decompositions was computational efficiency. Instead of doing things brute force, you can do them far more efficient. So for example, even the QR decomposition in problems of communication, you can potentially use the QR decomposition to do decoding much more efficient. Suppose you want to find the closest vector in some particular set. Then it turns out that you can use the QR decomposition, which is, for example, in decoding of multiple antenna communication systems. You want to do maximum likelihood decoding. There's this notion called sphere decoding, which again, it's computationally expensive, but far better than doing it brute force. All right. All right. So please go through the notes. There are some more details over there. The latest version is yet to be uploaded, but I'll do it by the end of the day. So what is our ultimate goal? We've now developed some of the background that we require, linear algebra and calculus. But ultimately, our goal is to solve minimization problems, general minimization or maximization problems, right? And in the unconstrained, if you don't have any constraints, suppose I just give you a convex function and I want to minimize this particular convex function, then, well, we can have a closed form solution. If we can have a closed form solution, we know how to do it. Basically, you compute the gradient, set it equal to 0, right, just as you did in high school. Find the stationary point, set it equal to 0. That gives you a local minimum, or if it's convex, then it gives you a global minimum. But in many cases, that is not possible. Right? So what can we do? We can use numerical methods like gradient descent, because we know that at any point, the gradient, the negative of the gradient is always going to point towards the point of minimum. So there are these numerical methods that you can do to just solve an unconstrained minimization problem. Now, then again, I'm not talking about the complexity of solving these problems, but just that it is doable, right? Now, suppose that we are posed with a constrained optimization problem. So closed form solution, you just set the gradient to be equal to 0 and that's done. Numerical methods, again, similar approach here. You compute the gradient and then you have this numerical procedure to find the minimum. But now suppose I give you a constrained optimization problem. So I have to do all of these, but under certain constraints. How do I solve these? I can't directly find the gradient set it to equal to 0, right? Because I also have to ensure that this point satisfies the constraint, which in many cases it won't. Right? So what do I do then? If I want to solve it numerically, I can't just do blind gradient descent, because I could be out of my constraint set. I have to ensure that it's still in my constraint set. Right? So the whole theory that we are going to try to develop is to solve constrained optimization problems. So what kind of constraints can we handle? And how do we design algorithms for these? Now you've seen a little bit of it when you've done Lagrange multipliers, but we'll try to go even beyond that. Right? So let's stop here. Right? Any questions?